Okay, let me just talk about a few other things. Okay, let's talk about confidence intervals. And okay, so what kind of conclusions can we make from a confidence interval? So let's say, you make a confidence interval for P based on a sample. Okay. So this is categorical data, right? If we can do confidence interval for P, let's say the confidence interval goes from, so we'll say 95% CI goes from, say, 0.47 to 0.55, okay? And this is proportion. This is P is the proportion that will vote for some candidate. Candidate A. Okay. All right. So when we get from 0.47 to 0.55, okay, or in other words, this is what, 0.51 plus or minus 0.04, right? Okay. 95% confident. Okay, can we say, what can we say? So you tell me, true or false, there is a 95% probability that candidate A will get 51% of the vote. False. Okay. Maybe, okay. How about this? There is a 95% probability that a future sample will have a sample mean between 0.47 and 0.55. Okay, also false. We are 95% confident that our sample proportion, the last statement should have said proportion rather than mean here. Confident that our sample proportion is between 0.47 and 0.55. This one's false, okay? Because it's a sample here, okay? And there's no, we're 100% confident that our sample proportion is 0.51, okay? Like, the sample proportion is just the value that goes right in the middle of our interval, okay? It's not, that's not correct either, okay? This needs to say population. If it said population proportion, that would be correct. How about we have evidence that candidate A will get over 50% of the vote. Okay, I will agree. Why is it false though? Yeah, so yeah, our 50% is in the interval, okay? So 50% is in the interval. Okay. Then, you know, if it was 55% plus or minus 0.04, then we would have evidence that the candidate will get over 50% of the vote, okay? But as long as 50%'s in there, then we don't have evidence that that this person will get over half the vote. Okay, so you know, I'll have some questions related to confidence intervals, and make sure you know the appropriate interpretations that we can make based on an interval. Yeah, question?
For the third one, you said if it had said our
population proportion, that would be true. Yeah, that would be true.
That's what confidence intervals are for.
Yeah, confidence intervals are, we're making conclusions about the population proportion, okay, based on whatever data we collected. Yeah, based on what we see in our data, we're trying to, not speculate's not the right word, but we're trying to make a conclusion about the population, okay? Okay. I do have, I don't want to call them trap questions, but they are questions where it is important that we check directionality for a hypothesis test. And I know this is not something that I've made you do very much in like quizzes or in your homework, but what does it mean to do a directionality check? Yeah, so with the directionality check, so, you know, we want to make sure that the data supports the direction of the alternative, okay? So if the alternative says mu1 is greater than mu2 in our data, we expect what?
Mean 1 to actually be bigger?
Yeah, we would expect y bar 1 to be bigger y bar 2, okay? And if that's the case, if so, carry on with the test. Okay, and if the data shows what? The opposite, then what does this tell us? Yeah, so this means, you know, our p-value, whatever it is, will be greater than 0.5, okay? And we will not have any evidence, to support the alternative. Okay, so I have a question or two on the final. Looking at this, I think, and I always warn students in the review session to watch out for it, but then always students miss it because I think in the rush of doing the final, they I don't know, forget this important aspect, which is well, it's important, you know, if you're doing any kind of data analysis experiment, you want to make sure that you're thinking about, you know, if you're hoping that the new drug is more effective than the old one, then when you collect data, it should appear that way, right? Because you know, in our in the research article with the St. John's wort, if anything, it appeared that it was less effective than placebo, right? So, okay, so I think that wraps up what I want to cover with the conceptual part. Let's maybe just do a quick review of all of the, well, I don't know if this is, if you feel like this is a waste of time, we don't have to do this. But I was going to do a quick review of all of the different tests that we've kind of covered, and kind of like, I don't know, well, I'll list off the formulas and the hypothesis tests, or hypotheses that are appropriate for each of these things, okay? So I guess I'll just kind of cover them in the order that we saw, okay? So first we'll start off with a confidence interval for mu, okay? And so this is y bar plus or minus t star times s over the square root of n, okay? T star has degrees of freedom equal to n minus 1, okay? And we just look to see if certain values. So I think we've covered confidence intervals enough that I don't need to write all of this other gibberish about, okay? And then we also have confidence intervals for the quantity mu1 minus mu2. Y bar 1 minus y bar 2 plus or minus t star times and then t star has degrees of freedom equal to n1 plus n2 minus 2. Again, this is an approximation. And if df not found, always round down. Okay, and then we have the t-test. T-test for independent samples. Null hypothesis is that mu1 is equal to mu2, or we can also write it as mu1 minus mu2, that the difference between these two means is 0. The alternative would be that there is a difference, or, you know, okay, and then there likewise the standard error is going to be s1 squared over n1 plus s2 squared over n2, and our test statistic is t y bar 1 minus y bar 2 over our standard error, okay? I think this is, I think this stuff is pretty straightforward, okay? Okay. We have the t. Oh.
What
On the final, is it then just a thing where we have to decide what to use, or in those moments, or do you kind of, is it?
So I will have like 5 questions set for deciding which test to use, and then when I have all of the kind of the data and all of that stuff, and you have to figure it out, then I'll tell you, do this test, okay?
So we
Or,
never do both.
huh?
We never.
Yeah, it's hard. It's really hard to write a test with multiple choice questions where it's like figure out what test to use, and not give away the next like
Right.
that answer and ask it like a related question. So I have to kind of separate it out. If it was like this open-ended question where it's like, I don't know, you write out all of this, then it's possible, but then it becomes really a lot of work for me to grade. So, okay, now I have the t-test for paired data. Great, thank you. Okay, so the t-test for paired data, your hypotheses here is that the mean difference is equal to 0, and then the alternative would be that the mean difference is not 0 or greater than 0 or less than 0. Okay. And here we have find d bar. Okay, and then you'll need the standard error is the standard deviation of that deviation column divided by the square root of n. So, okay, so standard deviation of the, the difference column. Okay, and then our test statistic is basically d bar divided by standard error. Okay, and then you have degrees of freedom equal to n minus 1. So this is for paired data. I want to make sure that the data is paired. Okay, and then you know, for data to be paired, you must have, like, it must be indicated that the data is paired as such. Okay. Okay, going back, you also have the Wilcoxon-Mann-Whitney test. Okay, with the Wilcoxon-Mann-Whitney test, our null hypothesis is that the respective populations produce values that follow the same distribution. Okay, and then the alternative would be that one of the populations tends to produce larger values than the other. Okay, that's again no symbols for the Wilcoxon-Mann-Whitney test because it's a non-parametric test, so no symbols here. And then, and what this involves, you know, kind of creating sample 1, sample 2, and then you have to count for each value, count how many values in the other column are smaller than that particular value. Right? For each value, count how many values in the other column smaller than that particular value. Okay, and then sum up those counts. Use the larger sum. Okay, that was our test statistic. And then look up that test statistic in the specific Wilcoxon-Mann-Whitney table. Is that okay? Okay, so t-test for paired data, Wilcoxon-Mann-Whitney. All right, and okay, so then now we have the categorical stuff. Okay, so we have confidence intervals for P, and we will say using the Wilson adjusted sample proportion P tilde, or P, and this is going to be y plus 2 divided by n plus 4. Our standard error is the root of p tilde times 1 minus p tilde over n plus 4. And then the resulting confidence interval, 95% confidence interval, is p tilde plus or minus 1.96 times the standard error. Thank you. Okay, and then okay, and then so all the related conclusions regarding a confidence interval work here as well. Then we have the chi-squared goodness of fit. Okay, and so here the null hypothesis is that kind of the probability of basically category 1 is equal to some value p1. The probability of category 2 is equal to some value p2, etc., etc., etc. And then the alternative is at least one of these probabilities is wrong. Okay. If you only have 2 categories, then you can have a directional alternative, okay? So if only 2 categories, then you can have directional alternative, and it would look something like this. The null hypothesis would be that the probability of basically p is equal to some value p1, and then the alternative will be that p is greater than some value p1, okay? And here, and I'm leaving off p2 because it's implied that that category 2 would be 1 minus this P1 and whatnot, right? So if you only have two categories, like you are something or you're not, and the null hypothesis is that we're expecting it to be like 30%, then it's implied that those who are not are 70%, okay? And that if the alternative is that the proportion is greater than 30%, then it's implied that those who are not, the alternative would be that it's less than 70%, okay? So with that, you can, the other group is implied, okay, or the other proportion with only two categories, it's implicit, okay? The chi-squared, so then you have to figure out your expected counts. Expected counts will be n times p of each group, whatever p, expected counts for each group. Okay, and then your chi-squared statistic is going to be the observed minus the expected count squared over expected, summed up for all groups. Okay. So you're going to need the expected counts for each group, n times p, for each group. And then you do the chi-squared statistic, okay? And then you'd look this up in the chi-squared table. Degrees of freedom is equal to number of categories minus 1. I forgot to do something. We have instructor evaluations. I have to do those. I think this. Well, let me hurry. I might come and pick it up before we're done. Okay, and then okay, so chi-squared test for independence. So here you've got some kind of table. It's probably going to be like A and not A, and B and not B. Okay? So this is going to be your observed table. So then here you'll need an expected table. Same thing, okay. And then the expected will be basically the row total times the column total divided by grand total. Okay. The null hypothesis is that A and B are independent, or symbolically we would write the probability of A given B is equal to the probability of A given not B, or something like that. Okay. The alternative is that they are not independent, and the alternative here would be that they are not equal, or greater than or less than. Okay. Same thing, chi-squared statistic, observed minus expected, squared over expected, summed up. Look up in the chi-squared table with degrees of freedom equal to rows minus 1 times columns minus 1. Okay, and then, okay, so now we have one-way ANOVA. The null hypothesis here is that mu1 is equal to mu2 equal to mu3. The alternative was at least one mu is different. Okay. Or, you know, however many groups you have. And then the way we calculate this is you have your source, and that's either going to be between the groups or within. Within is also the residual. Okay, degrees of freedom, n-1, so this is groups minus 1, number of groups minus 1, and then this is n minus number of groups. Okay, you have sum of squares. Here is the difference between each group mean and the grand mean. Okay, oh, maybe the grand mean is kind of the weighted average. So let me kind of separate that. That's going to be each group times its thing. You add those up, and you're going to divide that by the sum of the n. So it's kind of like the weighted average. Okay, so the sum of squares is the difference between each group mean and the grand mean squared multiplied by how many values you have in that group added up. Okay, does the n go? I don't know. It's multiplication, so maybe the formula is written with the n in the front over here. I'm not 100% sure. I feel like it is. Okay, and then over here we get to use the shortcut n minus 1 times s squared, and then we add this up for all of the groups. Okay, and then you have the mean squares, which is always the sum of squares divided by degrees of freedom, and then you have the F ratio, which is the mean squares between divided by the mean squares residuals. Okay, and then you look up. Now, you don't have, I'm not going to give you the F table, but if you did, you would look it up with numerator and denominator degrees of freedom, right? That's that for one-way ANOVA. So far, so good? I said so far, so good? So far, so good. Okay, and then lastly, we have a correlation. All right, and then so correlation first is 1 over n minus 1 times the sum of basically zx times zy, which turns into 1 over n minus 1 times 1 over standard deviation of x times 1 over the standard deviation of y times the sum of x minus x bar times y minus y bar. Okay, and I think probably it's best to do this with a table. X, y, x minus x bar, y minus y bar, and then, then the product, okay? And then you add those up. cetera, et cetera, et cetera. Okay. All right. To test if it is significant or not, you have rho equal to 0 versus the alternative that rho is not equal to 0, or rho is greater than 0, or rho is less than 0. And you have a test statistic which conveniently follows the t-distribution. N minus 2 and 1 minus r squared. Okay. Look up with degrees of freedom equal to n minus 2. And then lastly, for linear regression, okay, the line is in the form y hat is equal to b0 plus b1x. b1, the line of best fit, is always going to be r times standard deviation y divided by the standard deviation of x. And b0 is going to be y bar minus b1 times x bar. Okay. The best fit line runs through the point x bar y bar and minimizes the total sum of squares residuals. Okay, a residual is equal to the actual value of y minus the predicted value at that x. So we just say E is y minus y hat, but you got to kind of plug in the value of x associated with that y to get the predicted value there. Okay. And then, and r squared is our coefficient of determination. Which just tells us the percent of variation in y which can be explained by the model, which only contains x, okay? Which can be explained by x. I think that covers it. Yeah, absolutely. Okay, is everybody good with this page? Okay, let me just flip back a couple pages then. Chi-squared test for independence or goodness of fit?
Goodness of fit.
Here we are, goodness of fit. Okay, let me pass these out. I should have done these earlier, but here are your instructor evaluations. There's only a few of you today, but I hope you really, well, I don't know. I enjoyed the class. I'm gonna actually go ahead and stop the video here.